organizers for giving me the opportunity of presenting some of my work here and for making a nice conference that brings together superconductors and quantum gases. And so the topic that I will be discussing are these fermionic superfluids in the multiband case. And I will be looking basically at trying to set up an effective field theory to describe these. So with all the nice introductions that we've already had, I do not need to spend a lot of time on this, but nevertheless, since we are this interdisciplinary group, let me summarize and give you some fermionic highlights that are quite appealing. So, first thing is this, the observation of the pair condensation in the Fermi gases. It took place about 10 years after the Bose-Einstein condensation was observed in the quantum gases. And the reason for that is that in fact you would have to cool to much lower temperature below degeneracy before you would get pairing, but how this was done in the end was by using the Fishback resonances that we heard already about to boost DC to a formidable level of several percent, up to 10% of TN. And so that was first the observation of condensation of pairs, of strongly bound molecules, and later of the Cooper pairs. And then it took a little while longer, but not that much, before superfluidity in these Fermi gases was unambiguously demonstrated by rotating these gases and observing a lattice of singly quantized vortices, both in the DC and in the DCS regime. And since then, all the kind of tools that were successfully developed for the bosons were also more and more getting applied to these fermions, fermionic superfluids. And in particular, putting optical lattices and reducing the dimensionality. And this morning we heard even a nice new setup where you could focus on just a single layer of a fermionic superfluid. And there are some interesting things that can be done and controlled very well in the quantum gases that are much harder to do in our superconductors. And one is this imbalanced Fermi gases that you can think of as shifting the dispersion of spin up and spin down particles apart along the energy axis. But as we've heard, you can also shift them apart along the momentum axis and create a spin orbit. So, but in one respect, there is, at least to me, still a difference with the Bose gases, where you have a very successful description in terms of a macroscopic order parameter with the Gross-Mikhaevsky, and there's finite temperature extensions of that, such as this ZNG formalism. But for the fermionic superfluids, there is up till now nothing that has this breadth of applications and applicability in different cases. And so that's what we were trying to look for. And to be certain, there is already work done on this, and in particular, I'm going to compare with a Ginzburg-Landau equation that was set up for these fermionic superfluids a while ago by the first virtual speaker of this session, Salemero, together with Andrea and Engel. And another motivation that we had was to extend the reach of Ginzburg-Landau type of descriptions to lower temperatures, which was, we also heard about mainly yesterday by Shamenko, Milosevic, Peters, and Parov also presented this work. And that was done in the context of this multiband superconductors. So let me turn to the particular system that we had in mind to look at, and this is a four-component mixture of fermions, so that's still a bit challenging, the experimentalist, but we can reduce it to a single band system. So the four components here, they're coded by blue spin-up and spin-down atoms and red spin-up and spin-down atoms. I noticed that in the other talks, usually you pair up a blue with red, but here I'm going to have pairing interactions between the blues and between the reds. And so how this system is described is by an action functional over a fermionic field. So S0 is the free field part where you can change the masses and through the chemical potential set the different numbers and set some imbalance. And then we have these interactions, as I said, the pairing interactions, and there's also interatomic scattering going on between the reds and the blues. The type of interaction that's not in there is an interband pair scattering, where you would take a pair of blues and scatter them as a pair of reds. You can think of the blues and the reds, for example, as lithium and potassium atoms. It would make sense to include this case. So what we're after is, well, in some sense the partition function, but more specifically the thermodynamic potential of the system. And in this integral formalism, you write it as a sum over all the possible configuration of these fermionic Grassmann fields. And each of these configurations is weighed by the exponent of minus the action functional that was shown on the previous slide. Of course, you cannot take this integral because there's quartic terms, so we do the usual decoupling, introducing the pair fields, psi here. There will be two, psi 1 and psi 2, but you need two of them. And the idea is that if you would take now this action functional with this form of these pair fields and integrate out these psi's, you would get exactly back the previous result. In order to have this equality, we have to set this capital G1, G2, and G12. We have to relate them to the original interatomic scattering length of between these atoms, which in turn are related to the S-wave scattering length between these atoms. So these would be adaptable, but of course if you adapt them with a Feshbach resonance, you have one knob to tune the magnetic field, and they may not be adaptable independently.
Sorry, but why don't you have a pairing between fermion in one red and the other side? So you were making pairing between blue and red.
That's right.
This means that in an amplification you should have four spinner with four components and out of them.
Yeah, we can. So this would be possible by including additional collective fields, right? But this we could do by including them as density fields rather than pair fields. I can show you the longer description, but it would clog up the presentation here. So here I will focus on the pair fields. So there's many different ways of introducing these collective fields, and this is the way that we chose. So that if you do this integral, you get back.
So I guess what you're saying is that you have the up-down or the blue-red interaction, except there's no color flip.
There's no
No flip. Like
no taking two reds and flipping them into blues, right?
Okay, so flipping it.
Yeah. Think of the blues as lithium and of the reds as potassium. So that. Okay, so then the idea for the next step is, of course, now that you have written it in this way, it's become quartic in the fermionic fields, and you want to integrate these fermionic fields out. And you can do that formally and get this trace log of the inverse Green's function. But then you would be stuck if you keep things general. So these pairing fields now appear in this thing that I write down as F. And you can do this if this would not depend on position and imaginary time. And then you would obtain the usual mean field results, like the Mosey-Ashby thing, but with this little addition for allowing for imbalance. So instead of doing this, we use the gradient expansion. So we choose a local spot where we want to set up this description for the effective field. and have a constant value. This would be the constant value that you should determine self-consistently with the gap and number equations. But on top of that, we will allow for gradients in imaginary time and position of this f. And we included terms including the second order gradients here, right? So the idea is that we can calculate things when it's a constant that we plug in, but now we are going to take slow variations, this gradient expansion into it. And so the main thing is that now this is constant, but of course in this expansion these are also constants, and it's this tau and r dependence and for the quadratic terms that you have to take into account. And that's basically the main calculation that took place, that we did, where it was possible in the final result to collect terms with the different gradients in pieces that have the time derivatives and pieces that have the spatial derivatives, and to obtain this effective action. And so the main result for this effective action is written here, where so the gradients appear here, but the main difficulty is of course in calculating your coefficients C, D, and E in this case. But they are, it's possible to write them down in a rather simple form in the end, where you still have to do just one k integral, and they depend on this function f1, which is a nice nice function that you will recognize from imbalanced case, and also on the derivatives of this function. So note that the C, D, and E will still depend on the value of this background constant size of the order parameter around which you do the gradient expansion, and they depend on it through the E of k, the variable dispersion, where this is still. So that's the outline, and now in order to see whether this kind of gradient expansion is making any sense, I'm first going to compare it to some existing stuff in basically in a homogeneous case. And so there, let me start with the single band superfluids, where the main difference is now that we have an expansion around a finite value of psi that we have to calculate then self-consistent. The existing work that I already mentioned by Sademelo, Randaria, and Engelbrecht, they get their Ginzburg-Landau coefficients and functional by expanding around psi 0, which should be good for temperatures close to Tc. And so here you see the free energy as a function of temperature, and indeed when you look close to Tc, then the current formalism and the results that were obtained by Sademelo nicely match. Also in the BC region there is only a small change, but if you go to the BCS side, then you see that these coefficients that you get by expanding around this are giving you a big shift upwards, whereas if you keep this non-zero, then what we get at temperatures going to 0 is the result that you would obtain by including Gaussian fluctuations and calculating the free energy in the microscopic field. So, for the case of two-band systems, there we can see whether we obtain qualitatively similar features and characteristics as was obtained by the extension of the Ginzburg-Landau formalism that I mentioned before, which is it's a different extension. As mentioned by the speakers yesterday, this is an extension in the small parameter 1 minus T over Tc to a higher power. Nevertheless, the results are qualitatively very similar, so let me remind you what was found in their work is for these gaps as a function of temperature. You see that the order parameter for the weak band goes to 0 at the same temperature as that of the strong band. Nevertheless, there is this feature, this drop at the critical temperature that the weak band would have if it were just the only band. And this is also something that we find in our formalism if we look at these two order parameters, that there is this suppression near the TC of the weak band. This was termed hidden criticality by these authors, and they also have another way in which this appears, and that is through a bump or a peak in the healing length of the weak band system. This was obtained by Bourgeois, and here we look at the results that we obtained, and here we derive this healing length by putting a hard wall and then seeing how quickly these two order parameters yield back to their bulk value. You see the expected divergence for T going near DC, where also the ratio of these two healing lengths goes to 1. But as you lower it below the critical temperature, then we also find this peak near the critical temperature of the weak band, so this hidden peak. Okay, next we tried to see if this formalism will work for specific non-uniform systems. And so the first thing that we looked at there, or one of the first things, was dark solitones, because there was a very nice experiment last year by Zweeland's group at MIT, where they take one of these fermionic superfluid clouds and phase imprint half of them so that they get a step in the phase profile. And then what happens is that a dip in the density develops, and this will start propagating without changing shape as you expect for a solid. And in these trapped clouds, such a dip will oscillate in the cloud, and the authors determined this oscillation period, finding that it is very different from what you would expect from solid. So now that we have this action functional, what we can do is start plugging in some specific variational forms in it to see what's going to happen. For this dark soliton, we plug in a form like this, so you see that the shape gets conserved as the object moves. Psi infinity here would be just the background value of the order parameter. This A describes the dip in the amplitude of the order parameter, and theta will describe how the phase evolves as you go from one side of the soliton to the other. So if you plug in this specific form of psi in the action functional that I showed you before, then you can rewrite it as an action functional or Lagrangian density, which is equivalent for this field A and theta. And it has the form that's given here with the coefficients, this superfluid density, this quantum pressure term, and the kappa being linked to the C, D, and E parameters that I showed you before, which in turn still depend on the value of this amplitude. So that looks like a very nasty Lagrangian, but in fact, if you look at the equations of motion for these fields, they're integrable. Except it's not in the usual way where you get the solution of A in function of the position x, but you can express it in such a way that you will find the position x where this amplitude reaches a certain value. And again, this depends on these parameters. Once you have the A of x, so you can invert this relation, you can calculate also the profile for theta for the step in the phase. So let me emphasize that given this Lagrangian, then this solution is exact. Of course, in obtaining this action function of our Lagrangian, we made approximation, we cut off this gradient expansion. So what do we find? This is a picture for the density profile of this soliton, and we compare it to Bogoliubov-de Gennes calculations by Liao and Grant of 2011. And we see that we find a good agreement, especially for the slower solitons. This is, by the way, in the BEC range. Surprisingly, if we go to the unitary regime and we compare the dip, so how dark this soliton is as a function of the velocity of the soliton, then we find a very good agreement with this Bogoliubov-de Gennes calculations. Here we let the temperature go down, and by T 0.01 we already reached temperature 0. The agreement for the phase step is not that good. So, but still it's qualitatively okay, but it shows the limitation. We also looked at the energy as a function of the velocity of this soliton, and find that there we get, again, reasonable agreement. So the Bogoliubov-de Gennes is here for temperature 0, so you should compare it with the black curve here, and here this is the unitarity where there's still some distance. So if we can plug in a solitonic form, we can also put in a vortex type of profile and look for how this vortex core is shaped. There we can compare with the recent Bogoliubov-de Gennes calculations by Simonucci, Chieri, and Spinati, which were already mentioned earlier in this conference. And what we find is that we have good agreements, except now where if you combine BCS regime with the low temperatures, that would be, if you look at this blue curve here, that would be the Bogoliubov-de Gennes results, and then the black curve there would be what we have. You see the temperature is increased, the agreement is much better. Also here, if we go to this more BC regime, the agreement is again better. But for example, we don't get these Friedel type oscillations that the Bogoliubov-de Gennes gets. Finally, we can look at some collective excitations for the two-band system, because the soliton and vortex things that I showed you were single band, and this is a MultiSuper conference, so I have to show you also some two-band stuff. For this, we looked at the sound modes, and you can look at the in-phase sound mode, and the results here are plotted again as function of the temperature, where these upper and lower curves, they are the results for the sound velocity that you would have if the weak band or strong band were the only bands. Of course, this still depends on the size of the order parameter, so for that we included the coupling. But you see that the sound velocity that we get for this in-phase mode lies in between these two sound velocities. And moreover, also here there is a signature of this hidden criticality that you would have at this DC. In phase, let me end with the out of phase mode, where there have been some experiments in magnesium diboride that see a crossover from this top curve to the lower curve, and this has this twofold shape is also something that we find with our effective field theory. So with this, let me conclude that what I've shown you in 3 steps. The first was to advertise a gradient expansion for the fermionic superfluids where you expand not around zero but around a finite value that is self-consistently calculated. And that with this we compares well with the existing Ginzburg-Landau in the limit of t going to dc. And finally, I've shown you already some applications where we can compare with Bogoliubov-de Gennes and identify regimes where it works better and where it still needs improvement. Thanks for your...
Okay, we have some time here.
I have two questions about BCS-BC soliton. We consider the BC side. So one question is how much the phase profile is different from the Gross-Pitaevsky soliton.
The Gross-Pitaevsky soliton, but then you would have you would need to compare it with some Gross-Pitaevsky equation. So what kind of parameters?
If they just
So if you
was a gas with some S with Ketronet, you know exactly what is the profile. So I mean, if you compare it.
Yeah, and we have not compared. We have not compared this yet.
I think I can answer the question because for 1 over kf a equal 1 plus 1 Gross-Pitaevsky equation agrees pretty well with the PPG calculations already.
And so that would be the gross with 2a. So that would not be the 1 with the 0.6.
No.
Okay.
Okay, and the second question is how different the stationary soliton with the hard wall condition. In stationary soliton, there is a point where the density is exactly 0. So what happens if I just put a hard wall at this point?
To see if you would have a similar like of a
let's say the density.
Yeah, this is not something that we have done yet, but it's a good suggestion.
In the beginning you showed these two Cooper pairs, the blue and red, and if their Cooper pair interaction. This interaction is attractive or repulsive or inhibitive or
in the examples that I showed you, this was attractive, but I guess it can be tuned.
So if it's attractive, then this.
So the effective G's that appear for these fields, they depend on a combination of these interatomic interaction strengths. So there we consider both cases.
That there is 4-particle bound state form.
No, we do not take a 4-particle bounce. The possibility for a 4 or for a 3-particle bounce
But
state.
in principle, it is possible. Since I'm talking tomorrow about the quartet solution.
Well, I guess it would be principle, but so I know people looked at the case with a mixture of 3,
Yes.
with 3 fermions, right? And there is a competition between 3 body bound state, but there you have some additional frustration because if you want to make Cooper pairs, with the 3 you always have to leave 1 out. Here it's different. You can make everybody happy with making Cooper pairs. So I would expect that this 4-body bound state plays less of a role that I don't know for sure.
I think we have to stop here because we are quite out of time. So let's thank our speaker.
Very brief announcement because I've received a message that the gelato is melting. The first announcement is Andrea Ferrari made it look